Hello everyone. Today we're going to discuss an important topic from the subject computer organization and architecture. So our topic is complete instruction execution with examples. So we start by what are registers? Registers are a type of computer memory used to quickly accept, store and transfer data and instructions that are being used immediately by the CPU. So what are the registers used? The registers used are program counter, also known as PC, or it stores the address of next instruction to be executed. And instruction register, also known as IR, it contains encoded instructions.
The three important components in the field of computer architecture are the memory address register (MAR), the memory data register (MDR), and the multiplexer (the MUX). These components play crucial role in data transfer and routing within a computer system. Let's explore them one by one. First, we have the memory address register or MAR. The MAR serves as the temporary storage location within the computer's central processing unit CPU. Its primary function is to hold the address in the memory to which data is going to be transferred. Next, we have the memory data register or MDR. The MDR is closely related to MAR as it holds the contents found at the address stored in the MAR. When data needs to be transferred from the CPU and the primary memory, it is stored in the MDR. Now let's move on to the multiplexer or MUX. The MUX is the fundamental component used in digital systems to route signals from multiple sources onto a signal line of output. It acts as a digital switch, selecting and transmitting data from one of the several input sources to the output line.
Now let us look at the basic operational concept of the instruction cycle. The first thing that we would need to do is first instruction pointed by the program counter from memory to IR. So whatever address is stored in the program counter, we will have to go to that address in the memory and find out the content of that particular location in the memory and send this content to the instruction register or IR. Next, we will decode the instruction, then we will fetch the operands if required. Now, if our operation says that we have to perform a particular operation on the content of two registers, we will not need to fetch the operands from the memory as they are present in the CPU in the register itself. Next, we will execute instructions and finally we will store the results in memory if required. If not, then we will store them in the register itself.
Now, as we saw in the previous slide, the first step was to fetch instruction pointed by PC to IR. So how do we go about this? To do this, the first step that we will have to undertake is to transfer the content of the program counter to register to MAR. So whatever address is stored in the MAR, we will transfer that to the memory address register and we will generate the read signal. So we will tell the MAR to go into the memory and hunt for this location that is stored in the program counter and check what content is stored at that location. So obviously he'll need some time to do this. So while the MAR is performing this task, we'll have to wait patiently for the MFC. Now after we get this signal, the main memory will transfer the data that is found at that particular location in memory to the MDR or memory data register. So from the memory data register, we will send this to the instruction register or IR text. We will decode the instruction. So for example, if we have an instruction saying add R1 and R2, so what this means is we have to take contents to register R1, we have to take contents of register R2, add them and store the result in register R2. So to do this, first of all, we will take the contents of piecing and store them into the memory address register. Then we will ask the memory address register to hunt for this location and see what content is stored there and generate the read signal. So while it does it, we can do something productive in that time. Right, so what we do is increment the program counter register because previously we have learned that the program counter register must always point to the next instruction that is to be executed. So while we are waiting for the memory function signal, we will increment the program counter by 1. If it is a 4-bit computer, we increment it by 4. Then next, when the memory sends the data to MDR, we will take it and we will store it into the instruction register or IR. Then we will decode the instruction and finally execute the instruction.
Now let us understand these whole processes with the help of a diagram. So the first thing that we will need to do is take the content of PC through the bus and we will transfer it to the MAR. So PC out, MAR in. And we are taking the address, giving it to MAR and asking MAR to find this address and find the content what is stored at that address. So we are asking it to read whatever is stored at that particular memory location. Next, what we will do is waiting for MAR to complete this task. We will take whatever is stored in the program counter register and we will run and we will store it in Y. Now Y is one of the input of the multiplexer and the other input is the constant number 4. So this both the inputs and we have placed the select line at constant 4. So obviously the output A will also be a 4. Now here in B we will again transfer the contents of the register of the program counter register and now the inputs of the ALU are the constant 4 which is stored in A, and in B we have stored the initial contents of the program counter register. So we will ask the ALU to add them and the answer will be stored in Z. Now from here we will take out Z by Z out and we will store it in PCN, and then we will wait for the memory function completion signal. So now once we get this signal we will get data which will be stored in MDR. So from here we will take the data out and we will store it in the IR register. Now to the actual addition that we have to do from the contents of register R1 and R2. These are our general purpose registers from R0 to Rn-1. So we will take the content of registers R1 and we will store it in 5. Okay. So from here it will go to the MUX. It is one of the input of the MUX. The other is the constant 4. But this time we will select the constant Y and here we will get the output of the multiplexer as 1. So what content is stored in R1? Next we will take whatever content is stored in R2 and we will store it in B. Now we will ask ALU to add both of these and the answer will be stored in Z. Lastly we will take this out and we will store it in R1.
Arithmetical Logical Unit ALU, part of CPU that carries out arithmetical and logical operations on operands. WMFC, wait for memory function to be completed. Speed of the processor is greater than the speed of the memory. Thus it has to wait for the memory function to complete its task and wait for MFC signal that is sent when contents of specific location have been read.